Today, I want to look at the relationship between these two series, the sum I equal 1 to infinity, AI, and the sum I equal 1 to infinity of the absolute value of AI. It's worth commenting that if all of the AI numbers are positive, these two series are the same, and obviously if one converges, then the other one does. On the other hand, this can happen. If you look at the sum I equal 1 to infinity, negative 1 to the I plus 1, 1 over I, that's an alternating series with individual terms that are getting smaller and tend to 0. So by the alternating series test, that converges. On the other hand, the absolute value series is the harmonic series, a p-series with p equal 1, and that diverges. So it's entirely possible to have a series that converges and its absolute value series diverges. This is a thing that can happen. Is it guaranteed to happen, though? I'm going to look at that same example, except instead of 1 over I, it'll be 1 over I squared. Once again, because of the alternating series test, this series must converge to something. On the other hand, when I take the absolute value of each term before adding them up, that just kills any factor of negative 1. I get the sum I equal 1 to infinity 1 over I squared. This is a p-series with p equal to 2. That series converges. So in the first case, I have a series that converges, but its absolute value series diverges. In the second, I have a series that converges, and its absolute value also converges. If I look at an infinite series and I tell you it converges, that doesn't tell me anything about whether or not the absolute value series converges. In particular, the statement that if an infinite series converges, then its absolute value series converges too is not a reliable fact. In logic, if I have a statement if P then Q, and I interchange the P and the Q, the result's called the converse of the original statement. The converse of something, generally speaking, means something different from the original statement. So I am not sure at this stage whether or not this statement, if the absolute value series converges, then the sum of the AIs converge. I'm not sure if that's a reliable fact, a fact that's always wrong, a fact that's sometimes true and other times not. We don't know at this stage of the game. So let's investigate the consequences. In everything that follows, our presumption is that this absolute value series converges. My extra fact has to do with a number plus its absolute value. The absolute value of a number is either the number itself or the negative of that number. In the first case, if the number were 0 or bigger, for example, 7, 7 plus absolute value of 7 is 2 times 7. Absolute value of AI, after I add it to A, could give me 2 times absolute value of AI if the AI were bigger than or equal to 0. On the other hand, if the AI were negative, for example, negative 7, absolute value of that would be 7, and negative 7 plus 7 is 0. So really, there's only two things that can happen to me here. I could get 0 for AI plus absolute value AI, or I could get 2 times absolute value of AI. Nothing else can happen. At this stage of the game, it isn't clear at all why this fact will be useful to me, but it will be in a moment. Since AI plus absolute AI is either 0 or 2 times absolute AI, I don't feel bad about saying that AI plus absolute AI is between 0 and 2 times absolute value of AI. Now, our premise is that the sum of the absolute value AIs converges. That means that the sum of 2 times absolute value AI converges. By the direct comparison test, since the thing on the outside converges, the sum of the thing on the inside must converge too. So if the sum of absolute value of AI converges, then that tells me without doubt that the sum I equal 1 to infinity, AI plus absolute AI, converges. A person thinks, well, so what? AI is AI plus absolute value AI minus absolute value of AI. So if I want to start adding up AIs, it's the same thing as adding up these more complicated looking things. It looks like I'm making life harder on myself than need be. If the sum on the right converges, though, then the sum on the left has to converge because they're the same thing. It's too bad that I don't know that the sum on the right converges. I'd like to be able to split it up like this. Remember, though, these infinite series are limits. So when is it okay to say that the limit of something minus something else is the limit of the first thing minus the limit of the second thing? That's okay to do when both limits exist. The first smiley face indicates that we figured out that first sum exists just a minute ago. And the second smiley face is our premise that the sum of absolute value of AI converges. Both limits converge. It's legal to split the limit up into the separate limits. The first smiley face represents an actual real number. So does the second one. The sum, I equal 1 to infinity, of AI is the first smiley face minus the second one, the difference of two actual real numbers, which will be a real number. The sum of the AIs converges. So here's our conclusion. If the sum of the absolute value series converges, I guarantee you that the original series converges also. It's possible that the original series could converge, but the absolute value series diverges. The language used for that is conditionally convergent. That's a terrible name for this. It makes it sound like it doesn't really converge. If both of the series converge, if absolute value of AI converges, then that automatically tells me the other one does, and we call that absolute convergence. It's going to turn out that absolute convergence is the good kind of convergence. In the next video, we'll hit peak abstraction, and everything after that will get easier. In the next video, we're going to show that if you have an absolutely convergent series, you can pretend that it's just an ordinary algebra sum and rearrange any number of terms you want and get the same answer. Not just 3 or 4 terms or 5 terms. You could rearrange a literally infinite number of terms, and it won't make any difference. In the meantime, I hope everybody's having a good day, and I'll talk to you again soon.